Okay, here the recording in progress. Okay, so we are here, day before Thanksgiving. No class tomorrow, no class Friday for Thanksgiving. Everybody have a nice Thanksgiving. I'm done with 11.9. I'll give you the quiz, tell you what you need to do on it. It should be fairly easy, I would hope. You're gonna want you have your calculator handy. So this is all basically calculator dependent. So get your calculator ready to do stuff. And make sure you're in radian mode, not degrees. You want to be in radian mode for this. Okay, we only have two sections left, 11.10. I have the entire next week to do it, and then 11.11 the week after. Okay, so I'll introduce a little bit of 11.10 today, but not much. I probably won't do any problems with it, but we'll see how it goes. Okay, again, we're aiming for the last regular exam on Thursday the 9th, okay, which means Friday the 10th is probably just going to be question and answer office hour kind of thing. Okay, our final exam is Friday the 17th of December, 8:10 to 10:40. Just study the old exams. And I have office hours 8:10 to 10 on Tuesday, Wednesday, Thursday of finals week. Okay. All right, so here we go, quiz time. Let me show you ahead of time what you're going to be up against. So on page 768, okay, I've already done a problem involving inverse tangent. Here's the power series. Technically, it's also called a Maclaurin series. I'll talk more about that next week. Okay, but here's the power series expansion for sine x, cosine x. In fact, they give you the first four terms. So the author is using my rule of having at least four terms. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Okay, so sine x, x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. Cosine is 1. I like to think of it as x to the 0 over 0 factorial. So minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6 over 6 factorial. Okay. I'll just talk about it, but I'm not willing to write it down. You should know what they are, though. 2 factorial is 1 times 2 or 2. 3 factorial, 1 times 2 times 3 is 6. 4 factorial, 1 times 2 times 3 times 4, 24. And so on. Okay, so you just keep going for all these, and that's what you're going to need. And now here comes the quiz. I'll make it a little bit smaller. Okay, find the first four terms of the Maclaurin series of sine of 1 radian. Okay, I just showed you the formula. What was it? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Approximate to 3 decimal places. So you literally just punch in. You're plugging in 1. You're not going to get much easier numbers than 1, except for 0. Because if you plug in 1, look at sine and cosine. All the numerators are 1, aren't they? 1 raised to anything is 1. 1 squared is 1. 1 cubed, 1 to the 4th, 5, 6, 7. They're all 1. So the numerators are basically all 1. Then separately, punch out sine of 1 radian to 3 decimal places. Okay. If you did it the right way, these two should be the same to 3 decimal places. Okay, then same thing with cosine. So use the formula for cosine. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. You do have to figure out the factorials, right? I guess the highest you have to go is 7 factorial. That's easy to work out. 1 times 2 times 3 times 4, 5, 6, 7. Okay, and so use the first four terms of the Maclaurin series to estimate cosine of 1 radian to 3 decimal places. Then separately use your calculator to give the value of cosine of 1 radian to 3 decimal places. Once again, if you do it the right way, you should get the same answer. Very easy quiz. Okay, so I guess that's my Thanksgiving present to you guys, right? Okay, so do 11:59 p.m. tonight. It should not be that difficult, in my opinion. I showed you how to do an inverse tangent. the other day, right? Okay, both of these are alternating. So again, the theory is the series converges by the alternating series test. If you look at both of them, you plug in one. For sine x and cosine x, terms are alternating, decreasing the absolute value, and approach zero. Therefore, the series converges by the alternating series test. And if you stop anywhere, like after 4 terms, the error is no more than the next term. Okay, well, in each case, the next term is far beyond 10 to the minus third, which is all that's required for this problem. Okay, so you should get the same answer for the Maclaurin series, power series, and what you punch out in your calculator. Okay, therefore, it is possible. So I'm sort of done, but theoretically, you could wire your calculator. So if you ask yourself, how does a calculator do sine x, cosine x? It could, I'm not saying it does, not all calculators do this, but it is possible that the calculator just does this or this. It's all adding, subtracting, multiplying, and dividing. Hidden behind the scenes, there's no trig, there's no, all the funny stuff associated with trig and symmetry and all that. It can just punch this out. Okay, and theoretically, your calculator goes out to say 8 decimal places. Okay. So your calculator is set up so once it reaches a term that's past 10 to the minus 8, 0.00001, okay, then whoever wired it up said, okay, once you get a term that's less than 10 to the minus 8 by the alternating series test, I can ignore all the other digits and I would just present 8 digits or 9 digits or 10 digits or however many digits your calculator gives you by the alternating series test. Okay, you can use the alternating series test for this one, this one, this one. Notice you can't quite do it for e to the x. E to the x is not alternating. For e to the x, you have to do something else. And we'll learn that in the coming weeks after Thanksgiving. Okay, so that's pretty much about it. That's the quiz. I hope it's easy. You do need your calculator. Make sure you are in radian mode. And there you go. Okay, do it at 11:59 p.m. Okay. All right, I will introduce some of 11:10, not much, and then we'll quit. Okay, so what is happening in 11.10? Topic is Taylor and Maclaurin series, page 759. All right, suppose we start off with one of these infinite polynomials centered at A. Okay, so f of x equals this thing centered at A, c0 plus c1 x minus a plus c2 x minus a squared, blah, 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 blah. Okay. What we're going to do is plug in A and take a whole bunch of derivatives. So what happens if we plug in A? Well, all of these are gone, right? That's gone, that's gone. All I have is c0. So f of A is c0. Okay, take the derivative, f prime. That's gone. Derivative of this is c1. Derivative of this is 2c2 x minus a. Don't take notes, by the way. Derivative of this is 3c3 x minus a squared. Derivative of this is 4c4 x minus a cubed, blah, blah, blah. Once again, plug in A. Gone, 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 gone. So f prime of A is c1. Do it again. Take the second derivative. That's gone. This would be 2c2. This is 2 times 3. c3 x minus a. This is 3 times 4. c4 x minus a squared. Okay. Plug in A. Gone, gone, gone. So f double prime of A is 2c2. Okay. And you do it one more time. If you do triple prime, you end up with 3 factorial c3. You can continue the pattern. Okay. It ends up being the coefficients Cn is the nth derivative of f at A divided by n factorial. Okay. You can see a factorial growing 1 times 2 times 3 times 4 and so on. In case you're wondering you're not being tested on this, I'm just supposed to show you theoretically what happens. Okay. And then this is what you want. So page 760. If f has a power series representation at A, f of x equals summation n equals 0 to infinity, Cn x minus a to the n. at some radius of convergence. The coefficients are Cn equals Fn of A divided by n factorial. Okay. You don't have to memorize the derivation that I went over. You don't have to know it, but this is what you want to work with. Okay, so box 6 and 7 are what I would suggest putting on your cheat sheet. F of x is summation n equals 0 to infinity, Fn of A, n stands for the derivative, x minus a to the n over n factorial. This is called a Taylor series, centered at A. If A is 0, that's what we like, it's nicest. The name is called a Maclaurin series. So Maclaurin series is a special kind of Taylor series where you're centered at 0. Maclaurin series, you're centered at 0. Taylor series, you're centered at anywhere, A. So summation n equals 0 to infinity, Fn of 0, x to the n over n factorial. Okay, so it's f of 0, f prime of 0, x over 1 factorial plus f double prime of 0, x squared over 2 factorial. And there's a violation of my rule. I'll put the next one, f triple prime of 0, x cubed over 3 factorial plus dot, 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 just to show you 4 terms. Here we're centered at A. So instead of 0, you put A and x minus a squared, x minus a cubed. Okay. You're basically doing the nth derivative, exponent, and factorial. Okay. If you're centered at A, this is called a Taylor series. The one that we're most comfortable, and most of the problems that we're going to be doing, frankly, are the easiest case, the Maclaurin series. The Maclaurin series centered at 0. That table that we looked at, this thing that I had you write down, page 768, you'll need this for the quiz. You'll need this for the quiz. These are all Maclaurin series. They're centered at 0. So how do you know? If you're not centered at 0, it would be parentheses x minus 2 or parentheses x plus 5 or something like that. These are all centered at 0. Okay, so you use this for the quiz, use this for the quiz. You're plugging in 1, which means all the numerators are 1. You just have to figure out the factorials and then just add or subtract. And you'll know you get the right answer when you actually punch sine of 1 radian or cosine of 1 radian on your quiz. If you got the same thing, you know you got it right. And that's that, right? Okay, so I'll give you my version. And then we won't go much longer than that. Okay, so Maclaurin series, f of x is summation n equals 0 to infinity, Fn of 0, x to the n over n factorial. Okay. Believe it or not, if we were meeting face to face, I'd make you memorize this. Okay. I do have a technique to help you to memorize it. Okay. So my previous students before pandemic said, there's no way I'm going to memorize this. Well, there's a memory trick, DEF. We all know the alphabet, presumably. DEF, derivative, exponent, factorial. Derivative, exponent, factorial, DEF. Okay. So it's f0 of 0, x to the 0 over 0 factorial, f prime of 0, x to the 1 over 1 factorial, f double prime of 0, x squared over 2 factorial, f triple prime of 0, x cubed over 3 factorial, plus dot, dot, dot. Okay, so you're doing the nth derivative, exponent, factorial, dE over f. So you notice it's the 0 derivative. 0 derivative means the same function itself. Okay, and then first derivative, second derivative, third derivative. And then the exponent, 0, 1, 2, 3. Then the factorial, 0, 1, 2, 3. Notice very nice in this formula is it goes 0, 0, 0, 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3. So it's the 0th derivative, exponent, factorial. So notice again, we're indexing beginning at 0 most of the time, unless it's not allowed, like if you're dividing by 0 or taking the natural log of 0. But for the most part, we're now at the point where we're indexing beginning at 0. So it's the 0th derivative, exponent, factorial. First derivative, exponent, factorial. Second DEF. Third DEF. Okay. You can put this on your cheat sheet. Now, for a Taylor series, it's harder. Most of the time, we'll be doing Maclaurin series, which means we're centered at 0. It's a nicest case scenario. If we're off center, x equals a, the only difference is instead of plugging in 0, you're plugging in a, and you go x minus a. Think of it as a translation. You're just moving the graph, as it were. So it's still the nth derivative exponent factorial, only you're plugging in a, and you're going x minus a. So here we go. F0 at a, you don't plug in 0, you plug in a. X minus a to the 0 over 0 factorial. In case you're wondering, yes, this is 1. Yes, this is 1. So it's really just doing f of a, but this kind of follows the pattern. To me, if you were to memorize it, once you get this, once you have this one down, you get all the rest. Just replace 0, 0, 0 with 1, 1, 1, 2, 2, 2, 3, 3, 3, a million, a million, a million, and so on. Okay. So we can write any function which is infinitely differentiable in terms of these Taylor series, which is really nice. Okay, so what I would say is put this on your cheat sheet. It's equivalent to what I showed you in the text. You can put this also. And for your Taylor series, put this in your cheat sheet. And it's equivalent to what I showed you in the text. Okay, so I'll show you again what was in the text. So either way, page 760. Of course, the author has it nice and printed. My handwriting is not very good. Okay, so 6 is the Taylor series, 7 is the Maclaurin series. And remember our ground rules of writing at least 4 terms in your final answer for everything we do. Okay, and then just for fun, I will show you the derivation of e to the x. So write a Maclaurin series for e to the x. So we need to take derivatives of e to the x, but that's easy. All the derivatives of e to the x are e to the x, f prime, f double prime, f triple prime. Then I plug in 0, they're all 1. So that means for e to the x, here's the Maclaurin series. Whoops, where'd it go? Here's the Maclaurin series. All of these, the derivatives, are 1. Which means in the formula, just ignore this. They're all 1. I have x to the n over n factorial, our old friend. So summation n equals 0 to infinity, x to the n over n factorial, believe it or not, was e to the x. You might recall doing this a few sections back. Okay, we proved it by the ratio test. Okay, believe it or not, this is e to the x. Okay, now I didn't say it at the time. I kind of had to hold myself back, even though I'm kind of chuckling behind the scenes, where I knew this was e to the x, but I couldn't quite say it at the time to get you all confused. But now I can say it. Okay, x to the n over n factorial. That's x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial. Writing it in more conventional polynomial notation, 1 plus x plus a half x squared plus 1/6 x cubed plus dot, 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 go infinitely far. Believe it or not, that's e to the x. That could be a way your calculator computes e to the x, believe it or not. Now, by the ratio test, you could prove that the radius of convergence is infinity, interval convergence is negative infinity to infinity. So if you want e to any power, like e to the, I don't know, 0.5, just plug in 0.5, believe it or not. And that's it. Okay. So here's the power series expansion for e to the x. I sort of went over the derivation for that. And that happens to be this page now, 768, this one. Okay, we've talked about this. That was just a geometric series. I've shown you this by doing the Maclaurin series. I'll save these two for next time, but you have the formulas. I showed you this one because this was a geometric series of 1 over 1 plus x squared, and we integrated to get this. Okay. We'll do something similar for sine and cosine next time. I haven't shown you the derivation of sine and cosine, but here it is, and you'll be using this on the quiz. Okay, so here's e to the x. Again, you should be thankful, very appropriate on Thanksgiving season. Again, if we were meeting face to face, I'd make you guys memorize it. Okay, but it's basically just x to the n over n factorial. Okay, if you look back at a previous section, we did this and we proved it was convergent for all x. This happens to be e to the x. Okay, so some other side notes. Take a look. If I take a derivative of this, the derivative of 1 is 0, right? Derivative of x is 1. Derivative of half x squared is x. Derivative of 1/6 x cubed is 1/2 x squared. Okay. That proves the derivative of e to the x is e to the x. We get the same thing back. If you integrate, integral of 1 is x. Integral of x is x squared over 2. Integral of this is 1/2 x cubed over 3, which is that. Plus c, the plus c is where you can sneak in the 1. Integral of e to the x is e to the x plus a constant. Very interesting. And one more last tidbit, and then I'm just about done. Plug in 1. E to the 1. Put a 1 here, 1 here. E to the 1 is 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial. Okay, so you might think E is such a weird number. There's no rhyme or reason to it. There's a very nice formula for E. It's a summation of the reciprocals of the factorials. 1, 0 factorial is defined to be 1, plus 1 over 1, plus 1 over 2, that's 2 factorial, plus 1 over 3 factorial, 6, plus 1 over 24. Okay. This converges very quickly to E. E is about 2.7, right? That's 2 plus a half plus 1/6. So it's already 2.7, I'm guessing, plus 1 over 24. Okay, maybe just for fun, let me add that up. 1 plus 1 plus 1/2 plus 1/6 plus 1 over 24. Okay, it's already 2.708. And we know E is 2.71828. I'll show it to you. Let me punch E to the first power. 2.7. So this is the actual value of E. So if I add up infinitely many of these terms, I will get this. So nice thing about Calc 2, we've learned an interesting formula for natural log of 2. Don't memorize it if you don't want to. I showed you a nice formula for pi. Don't memorize it. And there's a nice formula for E also. There it is. Okay. All right, so I thought that was a nice way to end it. Okay, next time I'll show you more. I haven't done any problems with it, but we got plenty of time. I only have to do one section a week now. I just have 11, 10, 11, 11 to go. So mark these down, get going on the quiz. Schedule-wise, I'm already 11:10 and 11:11. So I have all of next week to do 11:10 and 11:11. Mark this off. You guys get working on the quiz and then have a nice Thanksgiving. Okay, so let me stop the share and check to see if anybody has any questions. And if not, that's it. See nothing in the chat. Okay, any questions, please? All right, so get working on a quiz and have a happy Thanksgiving, everyone. And we'll see you next time, next Monday. Okay, all right, have a good Thanksgiving, everyone. Thank you.
Happy Thanksgiving, Professor.
Happy
Thank you.
Thanksgiving. Okay, bye, everybody.